Hello everyone. Okay, so today we will discuss three important terms, which is prime implicant, prime implicants, and then essential prime implicants. All these three terms are used to find the minimum expression from the K-map. So in previous lecture we have already know that how we can find the minimum expression which is in form of SOP or POS using K-map. So we will use following criteria in order to find the minimum expression. So firstly we have to cover all the minterms, and secondly the simplified or minimum expression must contain minimum number of terms. Also, minimum number of literals must be there in each term. So these three conditions are used to find the minimum expression from the K-map. Okay, so we have used these three conditions in order to find the minimum expression from a K-map in order to find the minimum expression. Okay, so also we know that when a logic function is written in canonical SOP form, then this expression is always the unique expression. For example, this is your function that is written in canonical SOP form. So this is the maximum possible expression for this function. So whenever we use canonical SOP or POS form to represent any function, then these canonical forms are generally maximum possible expression. Okay, so do remember that this is the maximum possible expression for any function. Okay, so our motive is to find the minimum expression from the given expression. Okay, so also we know that whenever we simplify any function, we can consider don't care conditions can be either simply 0 or 1 according to our convenience, or according to find the minimum expression. Okay, so also one thing we should remember, that if any function is given, this is the order of the variables of this function. So we can draw the K-map like this by considering x is here and y and z here. So this is the order for the minterms. Okay, so 0 1 2 3 4 5 6 7. If we draw the K-map by considering x is here and yz is here, so order of minterms will be changed. So this will be the your zeroth minterm 0 1 2 3 4 5 6 7. Similarly, if there are four variables, if we draw first two variables here wx yz, so this will be the order for minterms 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Similarly, if we draw first two variables here, and then what will be the order of minterm? So it will be like 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So both the K-map are equivalent. Basically in these two K-maps, order of variables is different. So do remember, whenever you are plotting any function using K-map, then you can take any one of K-map. Okay, so both K-map are equivalent here also. Okay, so now we will come to the definition of what is implicant. Okay, so So firstly, I am giving you the formal definition of what is implicant, and then we will write a few results regarding implicants. So basically, if there is any function f on or f of n variable is given, then a product term p is called implement of f if for every combination of values of n variable, for which if p is 1 then f is also 1. So this is the formal definition of implicant. So any product term is called an implicant of f if for every combination of values of n variables, if p is 1 then f is also 1. Okay, if some combination of variables, if p is 1 and f is not equal to 1, then p is not the implicant, do remember. So just consider this example. If f is this function, then if this term is 1, then f is also 1, and if this term is 1, then f is also 1. So these terms are implicant of f. If we simplify this expression using Boolean algebra, we can get this expression. So these two terms are also implicant of f. So in case of implicant, we have to remember if any function is written in form of SOP, then every product term is an implicant. So if any expression is written in SOP form, then each term is an implicant of f. Okay, so we know that we can also write any function in canonical form or sum of min term. So every min term of f is also an implicant. So any term that is formed by combining two or more min term is also an implicant of f. Okay, so how you will identify the implicant on a K-map? So any single one or any group of ones which can be combined are called implicant of f. So basically, in case of implicant, firstly we have defined what is implicant, and then we have note down few results regarding what is implicant. Okay, and then we have also know that how we can identify implicant on K-map. Okay, so these three things we have to remember, that if any function is written in SOP form, then each product term is nothing but an implicant of that function. Also, every min term of a function is also an implicant. Also, any term that is combined by two or more minterms is also an implicant of f. So implicant is basically simple concept. Okay, so now we will move to another term, which is prime implicant. Okay, so what is prime implicant? We have to understand this. So any product term or any product term implicant is called a prime implicant if we cannot delete any literal from it. That means each prime implicant of a function has a minimum number of literals. Each prime implicant of a function has a minimum number of literals. Do remember. So any implicant is called an prime implicant if we cannot delete any literal from that implicant. So for the previous example here, we have called these terms as implicant, but from this term we can remove a dash easily. So this is implicant but not the prime implicant. So if we look into this expression, these two are prime implicants. So one thing we have to understand that prime implicant of a function has the minimum number of literals. Do remember. So any implicant become a prime implicant when it has minimum number of literals. Do remember. So in case of K-map, how you will identify the prime implicant? So any implicant is called prime implicant if it cannot be combined with another term to eliminate a variable. That means we cannot eliminate a variable from a prime implicant. So we cannot combine with another terms, because how we are eliminating the variable by combining the terms. So in case of prime implicant, we cannot combine it with another term. Do remember. Okay. Also, a prime implicant is obtained by combining maximum possible number of adjacent square in the map. So a prime implicant is generally obtained from the K-map by combining maximum possible number of adjacent square. But also we have to fulfill this criteria that further we cannot combine another term. Okay, so this is the basic definition of prime implicant. Okay, so we will look into how we will identify prime implicant from the K-map. So generally how we will find the prime implicant of a function using K-map. So simply that is very simple how to identify the prime implicants using K-map. So any single one on map represents a prime implicant if it is not adjacent to any other one. If there is single one on the map that is not adjacent to any other one, that one is called the prime implicant. Similarly, two adjacent one on map form a prime implicant if they are not combined in a group of 4. So if we have two adjacent ones that cannot be combined into that cannot be contained into a group of 4, then these two adjacent one are called will form the prime implicant. Similarly, four adjacent ones form a prime implicant if they are not contained in a group of 8, and so on. Okay, so basically we can find the prime implicant from a K-map easily. Okay, so consider this example. Okay, so I have solved this example here. So again I will write this question and then try to solve in front of you. Okay, so this is our first example. Okay, so this is our first example. Just suppose we have to find the prime implicant. We are focusing on how to find the prime implicant. Just suppose I am taking this one, and this one cannot be part of any 4 adjacent one, so it can be combined with this. So this is one prime implicant. These two are not part of any 4, so this is the prime implicant. Similarly, this is also a prime implicant because these two ones are not part of any adjacent 4 ones, so these are also a prime implicant. Similarly, if we look here, so this is also a prime implicant, but we cannot say that this is the prime implicant because these two ones are already part of a bigger 4, so these two are not prime implicant. Similarly, these two ones are not also prime implicants. So simple condition to find the prime implicant is any single one on map that is not adjacent to any other one is called the prime implicant. Two adjacent map form a prime implicant if they are not contained a group of four. Four adjacent one form a prime implicant if they are not contained in a group of eight. Similarly, we can proceed. So in this example, these two are prime implicant. This is not the prime implicant. This is not the prime implicant. So we can find out. So we can find out the all the prime implicants for a given K-map. We can easily find the all prime implicants. So suppose this is your example. So I will solve it again. So it is our given example. So if we look into this one, so it is part of this 4. So it cannot be part of any other no, cannot be part of 8 ones. So this is our prime implicant. This is also our prime implicant. Okay, so these two ones cannot be combined with any 4 ones. So these are also prime implicant. So so this is our these are our prime implicant. Also note that this is also our prime implicant, because these two ones cannot be combined with 4 ones. So this is also our prime implicant. This is also our prime implicant. These two ones cannot be part of any bigger cube. So these are also prime implicant. Similarly, these 4 ones are also prime implicants, will form the prime implicant. So in general, uh, we can find all the prime implicants of a given map, but whenever we solve a K map, we generally don't find all the prime implicants. We have to follow certain procedure to find the minimum expression for a given K map, but we can find all the prime implicants. How these prime implicants will be utilized to find the minimum expression, that is different concern, but still we can find all the prime implicants for a given K map. In these prime implicants, which we will choose to find the minimum expression, that depends. Okay, so we can easily find the prime implicants. Also do remember how these terms form the prime implicant, because we cannot remove any literals from these two. That means these two ones are not part of any bigger cuboid. Okay, so these two are also not part of any bigger cuboid. We are talking about these two. Okay, so we can find the all the prime implicants of a given function. Do remember. Okay, so now we will see how we will find the simplified or minimized minimum SOP expression. Okay, so we know that the simplified expression for any function will consist of some of the prime implicant of the function. Okay, so if we consider this example, we have find out all the prime implicants of this function, but the simplified expression will not consist or will not consist of all the prime implicants of the function. Okay, so we will use some prime implicants in order to find the simplified or minimum expression. Okay, so we can say that a minimum SOP expression cannot contain a term which is not prime implicant. We already know that prime implicant will be a term that is having minimum number of literals. So so if we are finding minimum expression, so there cannot be any term that is not the prime implicant. That means minimum expression will always contain uh, prime implicants. If there is any term that is not the that is non-prime implicant, that is non-prime term, then obviously we can combine it with another term to remove a literal. So it is clear that simplified expression will always contain only prime implicants. Secondly, we will use some prime implicants in order to find the simplified expression. We will necessarily will not use all the prime implicants. So in other in other words, we can say that we can find the SOP from a map. What we are doing, we will find a minimum number of prime implicants which cover all the ones on the map. Okay, so this requirement, a minimum number of prime implicants which cover all the ones on the map, that is exactly similar to our our basic definition of simplifying any expression. This definition is consistent with the previous definition which we are using, which is all the min terms must be covered. Simplified expression must have minimum number of terms and minimum number of literals. Because why it is equivalent to the fundamental definition? Because any prime implicant will always have minimum number of terms. So that is the criteria, that every term should contain minimum number of literal, because every prime literal always have minimum number of literals. And then we have minimum number of we have to find the minimum number of terms. So we have to choose minimum number of prime literals, and we have to cover all the ones. So all three conditions have been rewritten or restated in this statement. A minimum number of prime implicants which cover all the ones. We have to cover all the ones. We have to take minimum number of terms, and each term will have minimum number of literals. Since prime implicants will always have minimum number of literals, so we have to find out the minimum number of prime implicants. So this is again the same conditions we are stated in form of prime implicants. Okay. Okay, so we have in the point number 1 we have already told that because all of the prime implicants of a function are not needed in forming minimum SOP, therefore we need a systematic procedure for selecting prime implicants. So we will see how prime implicants can be selected in order to find the minimum expression. Okay. Okay, so in this example we have find out all the prime implicants of this map. Now we have to find out the minimum expression for this K map. So okay, so I will solve this. Okay, so this is our function we have given. So we can cover this one in this term by using this term. We can cover this one and this one. Okay, so these three prime implicants will be included in order to find the minimum expression for this. Okay, so this term is nothing but So here we have assumed A, B, C, D. So these are all prime implicants we have already know. So now we will take these three prime implicants. So we can write A dash B dash D plus B C dash plus AC. Why we have taken these three terms? Mm, uh, because we have to find the minimum number of prime implicants that cover all the ones on the map. So by uh, uh, so here we can see that we can cover all the ones by using these three terms. Okay, so uh, um, further I will explain you how we are selecting these three terms. So this is the solution for this question. Okay, okay. So also we can look at this example. Okay, so this example I have read on here. So this is the example 4. So here if we look into what are the prime implicants, so this one cannot be part of any 8 ones. So it is this. Okay, and this one can be covered by like this, and these two ones can be covered like this. Okay, so these are the prime implicants. There are other prime implicants also. This is also one prime implicant, but we have to take minimum prime implicants that cover all the ones. So if we take this and this, okay, so we will miss this one, these two ones, this one. So we can take we can select. So here all the prime implicants are, these four are prime implicants. So minimum solution will have this and this. Remaining ones are all already covered. So we can take these three terms. So while selecting the prime implicants in both the examples, what we are doing, there is we are not following any standard procedure. We are just somehow by observation or hit and trial we are finding the minimum number of prime implicants that will cover all the ones. So we are using hit and trial, and that method is not systematic. So in order to make the systematic procedure, we have to define some other terms also. Also we should note that if prime implicants are selected in wrong way, then a non-minimum solution may result. Okay, so in this example, if we select different prime implicant, then we may wrongly select the 4 terms. Okay, but minimum solution can be obtained by using 3 terms. So these two examples illustrate that we need a systematic procedure in order to find the minimum solution using prime implicants. So we will look into that procedure. Okay, so if we carefully examine the K-map, we can note that some of the minterms on map can be covered by only a single prime implicant, but other minterms can be covered by 2 or more different prime implicants. That means it is possible that few minterms will be covered by single prime implicants, while other minterms can be covered by 2 or more prime implicants. If we look from this K map, this is your minterm 2, this is your minterm 3. Minterm 2 is covered by this, and minterm 3 is covered by this and also covered by this. So we can say that I2 sorry, 1 min term 2 1 2. Okay, so min term 2 is covered by this min term, while min term 3 is covered by these two terms. So on a K map there are certain min terms that are covered by only a single prime implicant, while other min terms just such as min term 3 here is covered by two or more prime implicants. Okay, so now we will define another term which is essential prime implicants. So it is clear, if a minterm is covered by only one prime implicant, then that prime implicant is said to be essential prime implicant. If on a K map there are certain minterms that are covered by only one prime implicant, that prime implicants are called essential prime implicant. Also, uh, essential prime implicants must be included in minimum SOP. Okay, so whenever we are finding minimum expression using K map, then essential prime implicant must be included in the minimum expression. Okay, so just suppose this is your example, f of abc is minterm 0 1 5 6 7. So we can draw this function like here I have already drawn. So if we look into this one, this can be combined with this. Okay, no other one, it cannot be part of any bigger cuboid. Also it cannot be combined with any other one. So okay, if we look into this one, this can be combined with this, and this can also be combined with this, and similarly it can be also combined with this. So this one can be combined with this, and this also, this one can be combined with this and this. So if we carefully look here, so these two ones are only combined with are covered by only these two prime implicants. So we can say that minterm m0, which is this m0, is covered by only this term, and similarly m6, which is this, is covered by this term. So these two are essential prime implicants. Okay, so uh, so if a prime implicant cover a single minterm, then that prime implicant is called the essential prime implicant. Here these two are essential prime implicants. Do remember, essential prime implicant must be included in minimum expressions. So here firstly we have to identify the essential prime implicants, and then these two terms must be included in the minimum expression. Do remember. So these are the essential prime implicants. Okay, so here also this function is given, f of abcd. These are the, okay, so I have solved this question here, so you can look it at later stage, and now I will try to solve this question in front of you. So this is your given function f abcd equal to these minterms. So we have drawn this term like here. So now how we will find the essential prime implicant here. So if we look into this one, so this one cannot be part of any 4, it can be combined with this. So this is your essential prime implicant. Okay, and also if we look here, okay, so this minterm is covered by this prime implicant, no other prime implicant can cover. So I think so m0 is covered by this term. Okay, so now if we look into this one, just suppose, so this can be combined with this. So again, this minterm is covered by only this prime implicants. It cannot be part of any bigger cuboid. Okay, so if we look into this one, yes. So if we look into this one, this can be covered by this. Okay, so this minterm is also covered by only this prime implicant. So this is the essential prime implicant. If we look into this one, this is covered by this and this is also covered by this. Okay, so we cannot say whether it is essential or not. Okay, so if we look into here, so this M0, this M0 is covered by this term and this term is covered by this M11. M12 is covered by only this prime implicant and M6 is covered by only this prime implicant. Okay, if we look into the map, I3 is covered by two or more, one prime implicant this and another is this. Okay, so we cannot say that, we cannot say anything about this because of M6. We can say that this is the essential prime implicant. Okay, so there are these four are essential prime implicants. So we have covered most of the ones by finding the essential prime implicant. What we will do with remaining ones, we will look into that. Okay, so there are certain minterms that are covered by only one prime implicants. That prime implicants are called essential prime implicants. So again, we are not following any systematic procedure to find the essential prime implicant. So we will look into that, how we will find the essential prime implicant. For simpler problems, what we can say, in order to find a minimum expression. Okay, so this is our one rule. We first loop all the essential prime implicant in order to find the minimum SOP from a K map. We should first loop all the essential prime implicants. And how we will find out the essential prime implicant? So this procedure is for simple problems. We just look at once on the map and check whether how many prime implements cover that one. If there is only one prime implicant that cover the one, then that prime implicant is said to be essential. If there are two or more prime implicants that cover the one, then we cannot say whether these prime implicants are essential or not without checking other minterms. Do remember also, if a minterm is covered by only one prime implicant, then that prime implicant is said to be essential. If a minterm is covered by two or more prime implicants, then we cannot say whether these are essential or not without checking other ones. Okay, so this procedure is basically used for simple problems that is not systematic, and we just uh, uh, solve the problem by inspecting the ones that are covered by one prime implicant. So we need to develop a systematic procedure how to find the essential prime implicants. Okay, so how we can find the essential prime implicants? So we already know that if a minterm is covered by only one prime implicant, then that prime implicant is said to be essential. Also, in order to find the minimum expression, what we are doing, firstly we will loop the essential prime implicants, and then for remaining ones we will do certain procedure. Okay, so how we will find the essential prime implicants. Okay, so in order to find the essential prime implicants, we will use this theorem. Okay, so according to this statement we will proceed. This theorem can be proved and by the method of contradiction. So it is out of scope to prove this theorem here. So we will consider this as the standard result, and then we will try to solve the questions by using this theorem. So what is the statement of this theorem? If a given minterm and all of the ones adjacent to it are covered by a single term, then that term is essential prime implicant. This is the statement of this theorem. If a minterm and all the ones adjacent to it are covered by a single term, then that term is essential prime implicant. Okay, if we consider the reverse of this theorem, that is not true. For a given term, if all the adjacent ones are not covered by a single term, then two or more prime implicants will cover that minterm, and we cannot say whether these prime implicants are essential or not without checking the other minterms. Okay, so the negation of this theorem will not always be the true. Do remember, if a given minterm and all the ones adjacent to it are covered by a single term, then that term is called essential prime implicant. If all the ones are not covered by a single term, then we cannot say that. So we cannot say whether the terms that are covering the one is essential prime implicant or not. Okay, so do remember this theorem. Okay, also in this theorem, if don't care conditions are present, then how we will deal with the don't care conditions. Okay, so firstly we don't have to check to see whether don't cares are covered by one or more prime implicants. So we will not focus on the minterms. We will not focus on the don't care conditions to check whether these don't cares are covered by one or more prime implicants. Okay, we will check for ones only, not for the don't cares. Also, while checking a one for adjacent ones, to find the adjacent one, we will consider don't care as ones here. Okay, so because don't cares can be combined with ones in process of forming the prime implicants. So in this way we will deal the don't care conditions. Okay, so we will see the examples of this theorem, how to find the prime implicants. So firstly I will uh, write the pseudocode or algorithm for that procedure, and then we will do few questions. So this is the statement, this is the standard procedure. Step 1, in the step 1 we will choose a minterm, any minterm which has not been covered yet. Okay, so we will check, we will choose a minterm. Okay, in step 2 we will find all ones and x don't cares that are adjacent to that minterm. Okay, so we will choose a one that has not been yet covered, and then we will find all the ones and x that are adjacent to that minterm. Do remember that in a n variable map there are n adjacent square for any square. So if there are n variable, so there will be n adjacent squares to any minterm. Do remember. So in step 2 we will find all the ones and x which are adjacent to the minterm. Okay. Again in step 3 we will check if a single term covers that minterm and all the adjacent ones and x, then that term is essential prime implicant, so select that term and loop it. So this is the statement of our theorem. We will how we are doing, we will select we will choose any one, and then we will find the adjacent ones and x for adjacent ones and x for this minterm, and then if there is a single term that covers the minterm and all of the adjacent ones and x, that term is essential prime implicant. Also I have written here, note that don't cares are treated like ones in step 2 and 3, not in step 1. What is the meaning of this note? So how we are dealing with don't cares in this procedure? We will not choose any don't care. Now whether it is covered by one or more prime implicants. Okay, but whenever we have selected any ones, and then we are trying to find the adjacent to that one. So then in that case we will consider x as ones. Okay, so that's why I have written that don't cares are treated like ones in step 2 and 3. Step 2 and 3, while we are finding the neighbors of any ones, in that case we will consider don't cares as ones, but we will not look into finding whether a don't care is covered by one or more prime implicants. Okay, so after and then we will repeat step first, second, third until all the essential prime implicants have been chosen. So after selecting all the prime implicants, we will repeat these 3 steps. Okay, for the remaining ones, what we are doing, we will find a minimum set of prime implicants which cover the remaining ones. For the remaining ones, for a minimum set of prime implicants we will find that will cover the remaining. Okay, so okay, I will explain the procedure by using few examples. Okay, so this is also the flow chart. Okay, so same algorithm I have written in form of flow chart. So we will start by choosing a one which has not been covered, and then we will find all the adjacent ones and x to that one, and or the if or the chosen one and its adjacent ones and x are covered by a single term. If yes, then that term is essential prime implicant and loop it. Okay, if it is not true, then we will check whether all uncovered ones are covered or not, are checked or not. If not, then we will again choose one. At this step if we look carefully, all the prime essential prime implicants have been determined. Okay, for the remaining ones, what we will do, we will find a minimum set of prime implicants which will cover remaining ones on the map. So this is the flow chart for the given procedure what we have written already here. Okay, so now we will look into the examples of this procedure. Okay, okay, so if your function, if this is your k map, so I'm redrawing this k map, and then we will find the essential prime implicants using the algorithm which we have stated. Okay, so this is the given k map. Okay, so if we look into this one, what are the, this is 4 variable k map. Yes, so for any square there will be four adjacent squares. Okay, so if we look at here, so what are the neighbors of this one? This here, that means here, these four positions are the neighbors. So we have the neighbors at this position, no one is present, these two positions are occupied. Okay, so here also this one is it possible to cover these three ones which are neighbor of this one along with this using one term? It is not possible. So this cannot be the essential prime implicant. Okay, if we look at this one, yes. So this and this, these are the four neighbors. Here no one is present, no one is present, so these two are the neighbors. So with respect to this one, all the neighbors of this one can easily covered by a single term like this. So this is the essential prime implicant. After choosing the essential prime implicant, we will focus on those ones that are not covered. We will not focus on these ones. Okay. So now again we will choose a one. Okay. So if suppose I choose this one, well, so I will look into this one, and then what are the neighbors of this? Yes. So here no, nothing is present, here no. So this is the only neighbor. So this is again the essential prime implicants. Okay, so we will not focus on this one. Okay, so now again if I focus on this one, this is having only one neighbor. So this is also can be covered by single one. So this is also essential prime implicant. Okay, so one, these are the two neighbors, but these two neighbors cannot be covered by a single term. So it is not a part of any essential prime implicant. So clearly we have essential prime implicants like this. Okay, so for the remaining one, according to our algorithm, what we are doing for the remaining one, find the minimum set of prime implicants which covers the remaining one. So after choosing the essential prime implicants, for the remaining one, we can see that this one cannot be part of any four. So it can be combined with this or this. So these are the essential prime implicants. These must be included in SOP. Yes. So this one can be covered by using this or this. So there are two possible solutions for this function. These terms are essential. This must be part of any minimum expression, and any one of them can be chosen. Okay. So in this way, also we can note that choose a one. So choosing here we have to choose a one, and we have to look into the neighbors of that one. So here if we carefully choose the ones, then this algorithm will be very simple. Okay, so we have to cleverly select ones that so that we can find all the essential prime implicants. Okay, so if we look into this question, find all the minimum SOP expression for the followings. Okay, so there are two parts. Okay, so this function FPQR is pi m234. So we can write this function PQR in form of SOP. So we can write summation d remaining terms. Okay, so if we draw on K map, if we draw this on K map, we will find this. Okay, so we look, this is a 3 variable K map. So for any square, what will be the maximum number of neighbors? It will be 3. Okay, it will be 3. So for this one, this and this, here this means there. So this is the neighbor. Okay, so this is the only neighbor. It can be easily covered by this. So this term is essential prime implicant. If we look into this one, okay, so these two are neighbors, it cannot be covered, so it will not result into any essential prime implicant. Here these two are neighbors, cannot be covered by single one. Here this one has only one, so this is the essential prime implicant. So for after finding the essential prime implicants, for remaining ones, we have to find out the minimum set of prime implicants that cover the remaining ones. So it can be combined with either this or this. So what we have done, so these are the essential prime implicants. It can be combined either with this or this. So in this way, we can find the uh, all the minimum expression. So these two terms will be included, and we can add PR or Q dash R corresponding to these two. Okay, so in B part we have given some don't care conditions here. Okay, so this is your given. So I have drawn this here. Okay, so this is the given one. So according to procedure, we will not choose any don't care. Okay, we will choose a one. Okay, that's why I have written that in the procedure don't cares are considered as one in step 2 and 3. Okay, not in the step 1. Okay, so if we choose this one, yes, so what are the neighbors? Here only 3 neighbors are, so one is present, so it can be covered by this. Yes, so this is the essential prime implicants. If we choose this one, this is the neighbor, here no one is present, it is the possible neighbor, so these two are the neighbors of this one, it can be covered by single one. So there is no remaining ones are there. So what will be the solution? Essential prime implicants corresponding to this term is this, corresponding to this term is this. So there is no, so it will be the unique solution for this question. Okay, so now we will look into an example which consists of 4 variables. So this is the given expression. So we have to find out the minimum expression, and based on our procedure. Okay, so I have redrawn this question here. Okay, so we have to find the essential prime implicants firstly. So if we took this one, what are the neighbors? Here nothing is present, this is the only neighbor, so clearly only neighbor can be covered by this, so this is the essential prime implicant. Okay, if we look at this one, yes, so these 3 neighbors are absent, only neighbor here which is here, so it is also essential prime implicant. Okay, if we look into this one, this is having only one neighbor which can be covered by this term. If we look the neighbors of this one, these two neighbors cannot be covered by the single term. Okay, so if we look at this one, firstly we have to identify all the essential prime implicants. This one has 3 neighbors which cannot be covered by a single term. This one has these 2 neighbors which can be covered by, so this is also essential prime implicant. So in this question, if I have selected all the essential prime implicants, for the remaining one which is here only one, so it can be combined with either this or this. We have to find the minimum number of prime implicants for the remaining ones, do remember. So it cannot be part of any 4, so it can be combined with these 2 ones. So solution will have these 4 essential prime implicants, either this or this. So based on our procedure, we can systematically find the minimum solution for the given expression. Okay, So now we will look into another example. Here some don't care conditions are given. Okay, so I have drawn here also this. If we look at this one, what are the neighbors? Yes, what are the neighbors of this one? This and this. We cannot cover these three with this, so it is not part of any essential prime implicant. Okay, so if we look here, this one, these three, this is also never. So these 3 4 and this cannot be covered by single one, so it is not the essential part of any essential prime. If we look at this one, these three neighbors cannot be covered by a single term. Similarly here, if we look, these two and these three are neighbors, so it cannot be covered by single term, so it cannot be part of any essential prime implicant. So if we choose this one, yes, if we choose this one, what are the neighbors? Here nothing is present. Here they means here no, nothing is present. These two are neighbors which can be covered by a single term. So the only essential prime implicant here is, which is, what is this term? A dash B. Okay. After finding essential prime implicants, we have 4 remaining ones. So these 4, we now, based on the last step, for the remaining ones, find a minimum set of prime implicants which cover the remaining ones. So for these 4 ones, we have to find the prime implicants that cover these 4 ones. So there are again many possibilities here. So F, we can choose this and this prime implicants along with this prime implicant, B dash C plus BD dash. In this way we can cover these. So solution will be essential prime implicants plus BC dash plus BD dash, which is A dash B plus BC dash plus BD dash. So essential prime implicant can be included with these two terms. Also, if we look carefully, this is our essential prime implicants. Remaining 4 can also be covered by like this and this. Okay. Similarly, this is the essential prime implicant. Remaining 4 we have to cover. We can cover these two ones by using this and these two ones by using this. So this is also one possible. So basically there are three minimum expression possible for this K-map. Do remember, firstly we will find the essential prime implicant which is part of every solution. Okay, after finding the essential prime implicants, then for remaining we have to find the set of minimum prime implicants that cover remaining ones. So that is all about. So basically we have learned 3 terms. One is prime implicant, another one is prime implicants, and then prime implicant, then essential prime implicants. Okay, so how also we have learned that essential prime implicant must always be part of minimum expression. Also, minimum expression cannot contain the term that is not the prime implicants. We also seen this. Okay. And in order to find the essential prime implicants, we have to follow this procedure. So this procedure is important after practicing few questions. So you are able to find the essential prime implicants directly. Okay, after finding the essential prime implicants, then for remaining ones we will try to cover we will try to find minimum number of prime implicants that cover the remaining ones. So that is all about today's lecture. Okay, thank you.